Hello, everyone. Thank you for joining us today for this USEA consensus webinar, Increasing CO2 Storage Options with Injection of CO2 in Shales, featuring Advanced Resources International. My name is Alex Krauka. I am a Seattle-based consultant with the U.S. Energy Association's Consensus Program. For those of you who may not know, the Consensus Program is a cooperative agreement with the U.S. Department of Energy's Office of Fossil Energy and Carbon Management. The program was founded in 2008 and seeks to educate the public, policymakers, industry, and other stakeholders and build a consensus on the wide array of benefits of carbon capture, utilization, sequestration, as well as other carbon management technologies. So things such as direct air capture, blue hydrogen, rare earths, critical minerals, and the like. We do this through a series of activities, such as briefings and webinars, such as the one that we're hosting today. We have workshops throughout the year. Of late, as with everything else, those workshops have been virtual. However, in non-COVID times, many of them were in person. We also produce a series of reports throughout the year, such as the one that we'll be discussing today from ARI and EORI. They've done some great work, and we're very excited to share that with you. And then finally, we have a monthly news clips that we put out to help our stakeholders stay engaged, stay informed of industry happenings. If you are not on our mailing list and you would like to subscribe, please feel free to email my colleague, Michelle Littlefield at mlittlefield@usea.org. Now moving into the topic for today, before passing it on, I just wanted to give everyone a visual here. This is a map of CO2 facility emissions within the U.S. And kind of the areas that we'll be talking about today is this right here. As you'll see, a decent amount of CO2 emissions coming from these areas. If we are to meet our decarbonization goals, we're going to need to do something with those emissions. And so we're pleased to host ARI and EORI today to present the results of their study, which will show a significant amount of space where we can store those CO2 emissions. Interesting fact that I got from the study is that the amount of CO2 emissions that could be stored in the areas that we'll be discussing today is approximately the equivalent of the emissions from a billion, that's billion with a B, cars, which is about the number of cars in the U.S. or the emissions from cars in the U.S. for approximately 9 years. So this is really a really significant amount of CO2 that could be stored in the shales that will be discussed today. So very excited to be hosting this. With that, I'm going to pass it over to USEA's Consensus Program Director, Mike Moore, to discuss a little bit more about this study, its genesis, how it came about, and then he will introduce our speakers for today. With that, the floor is yours, Mike.
Alex, thank you very much for the introduction on that and what we're getting ready to do with the presentation here. The study that we're going to talk about is about CO2 and shales. Earlier on, before market shifted, it was what kind of work could CO2 do just strictly to go in and do more work for oil production. And it kind of became the idea that you're going to have a lot of wells permitted under new rigorous permitting requirements in wide open areas where these shale basins are and have been produced from, or expect to say maybe future production, that they have another purpose, the ability to not only enhance some potential oil production, but actually become useful storage facilities after the first wave of oil production has taken place. In other words, you're taking advantage of a system that's covered its bases already, and you got a new place to put it. And you're going to find yourself in areas where there's maybe not some quality sequestration capacity otherwise available. It can change the calculus of a firm's decision-making on what it does with its businesses, with its practices and CO2 capture and its opportunities. It also presents potential future value for the landowners, mineral holders, and the state's revenue streams as well, reviving assets that have been played through as far as you might otherwise have gotten them. Now, I'm not going to go any further with this. I'm going to say to both Graham and to Vela. Vela, it's been an honor to run and work with you for at least 20 years, and always a pleasure to work with you on things. Graham, great to meet you. I hear a lot of great things about the work up there. You're with the Enhanced Oil Recovery Initiative up in Wyoming. And with that, Vela, I'm going to turn it over to you and let it go.
Thank you, Michael. I appreciate the opportunity to present, and thank you for the introductions, Mike and Alex. And Mike, I like your picture. Very, very classy behind your screen. So I'm going to talk about just really what Mike said. How much can we store in shales, and we're going to look at 3 basins, roughly in the middle part of the US. Next slide, please. Oh. Joyce, can you move the slide? Or thank you. All right, I can do it. So the 3, we're going to start out with some introduction, and then we're going to look at the Niobrara Shale in the Denver geologically Basin, north of and west of Denver, the Cana-Woodford Shale in the large Anadarko Basin, and then the Mowry Shale, which Graham is going to talk about, in the Powder River Basin. Next slide, please. I've said that we're going to look at these 3 settings, and in a sense, Alex already kind of stole my headline at the bottom of this slide, which is there's enough space here for taking the emissions from over 1 billion passenger vehicles for 1 year worldwide. And that equates to basically 4,600 million metric tons of storage capacity. To make it simpler, 4.6 billion metric tons. Particularly, I want to just stress again, these shales tend to exist in places where the saline formation storage capacity is limited or still rather poorly defined. Next slide. Can I get the next slide? Thank you. I need to go back 1. Good, thank you. This just, whoops, great. When we start out on the storage side, I'm going to give you the summary results, and then we're going to follow up with the details that hopefully make you comfortable that we've done our homework. And so about a 1.5 billion would be in the Niobrara Shale, the DJ Basin, about 1 billion of it in the Cana-Woodford Shale and the Anadarko Basin, and a little over 2 billion metric tons in the Mowry. And on the right-hand side, we were going to show the amount of oil that we would recover. And that's basically 3.3 billion in the Niobrara, 1.7 in the Cana-Woodford, and 1.9. And you can quickly take a look that if I divide the 4.6 billion metric tons by the almost 7 billion metric tons, we're going to have well over a half a metric ton of CO2 stored per barrel of oil. And that's going to become quite significant. Next slide. And this ties in right back to this topic of carbon management and things that we can do to enable the consumption of lower carbon intensity oil. First, of course, if you could produce lower carbon intensity oil, then that gives you that opportunity to consume it. So we went back to some fundamental life cycle analysis and built up the total carbon that would be released by producing and consuming 1 barrel of oil. And I'm going to use kind of the scientific terms, 87 grams of CO2 per megajoule. Later on, I'll show you really how that translation takes place, but that includes 11 grams that covers the extraction, refining, and the transportation parts of that barrel of oil. 3 grams that are add to that by doing an EOR process, primarily from the compression that's required for the re-injection and the injection of the CO2. And the biggest part, well over 80% of the carbon, comes from when that barrel of oil is consumed, either as gasoline or diesel or jet fuel and so on. Now, the good news is that in these 3 basins, you can store on average 109 grams of CO2 per megajoule and that much is stored for every barrel of oil that's produced. So if I start with the 87 grams and subtract the 109 grams, what we have is a potential for actually producing carbon negative intensity oil. And just to give you a comparison, imported oil has a positive carbon intensity of 85. Next slide, please. And so this shows the results by the basins. In the Niobrara Shale, it is slightly positive, about 12 grams megajoule. Go to the Cana-Woodford, it's slightly negative. And the Mowry Shale, which Graham is going to talk about, really provides a wonderful place to store CO2 and bring out low carbon intensity oil. And there's some conversion factors at the bottom of the slide that once you go home, you can kind of work out the numbers for yourself. Thank you. Next. Okay, so I want to give you a little of the background of how we did the studies. And as I said before, so you have some confidence in the results. Next slide, please. I'm going to start out with the Niobrara Shale. You can see it on the map on the left, where you see the kind of the Denver area, roughly in the southern center of that basin area. And it's a Cretaceous age, a series of chalks and marls, as shown on the right-hand side, that are developed by drilling horizontal wells and intensively stimulating those wells. Next slide. We had to put together some critical reservoir properties. Shale depth, of course, an important one. And what you see is the basin gets shallow on the east around 5,000 feet, and then really begins to reach around 10,000 feet along the west. And then on the right-hand side, you see the thermal maturity. And this is really tells you how much of the shale, the organic matter in the shale, has been cooked. And the higher the thermal maturity, the lighter the hydrocarbon. We're still mostly in the oil window here, maybe slightly getting into the gas window, right into the center of that blue area itself. But that establishes one of the major partitions or areas of this basin. I'll discuss that because we're going to carve this basin into 3 very geologically distinct areas. Thank you. Next slide. This gives you a quick glimpse of, just like what Mike was saying, it has been drilled, and for about the six, 7 years, over 1,000, roughly 1,000 wells per year, horizontal wells, have been drilled and placed on production in this basin. And you can see the dark cluster, the cluster of dark dots that is roughly in that higher thermal maturity area. And the play has progressed to the east and to the north, and those define our other two partitions or geologic settings. Next slide. For each of these settings, we put together a type well. This one is for that core area, that high thermal maturity area. Represents 814 recently drilled wells in this Wattenberg core. The well area covers 128 acres, has a horizontal lateral about 8,500 feet, a net pay of about 200 feet. And on primary production, you would expect the gross oil recovery, EUR, of about 260,000 barrels. And you can see that, you know, after about 5 years or so, 6 years of production, production really starts to fall off relatively rapidly. Next slide. So these are the characteristics for the three areas. The total area is, for the Wattenberg core, is almost 2,000 square miles. We de-risk that area as wells are developed. And this shows you some of the other reservoir properties. You can see at the bottom, with producing gas oil ratio, you get about 8 MCF per barrel in that whole area. And right in the center of that thermal maturity, it's higher than that. And then you have an eastern extension area and a northern extension area. And we're going to apply the same methodology to each of these areas to establish the storage capacity and how much we recover. Next slide, please. We used a rather sophisticated reservoir simulator. It's GEM from the computer modeling group. It's a full-scale model that looks at both the grid blocks, but also looks at the composition of the shale oil itself. We first used it to history match so that we had confidence that the reservoir properties we were looking at, and also that the stimulation methods, what we called SRV, or the stimulated reservoir volume, also matched the production from the well. What we've shown is one segment of that modeling. Next slide. And these are the dimensions. On the top, you're basically looking down on this segment of the well, and you can see the horizontal well. And what we determined from the history matching is that the stimulated reservoir volume extends about 250 feet on either side of the horizontal well. It doesn't go all the way across to where the next well would be on the outer edges of this block. And then when you look at it from the side, in basically B, you can see the entrance of the well, and you can see the stimulated reservoir volume went up about 140 feet out of the 200 feet of net pay that we analyzed. And what's so critical is, if you look at the table on the right, is that in the stimulated reservoir volume, you raise the permeability to about 0.14 millidarcy, about 1/10 of a millidarcy, as opposed to before it is stimulated, something like 5 to the 10 to the -3. So you're looking at raising the permeability by over 2 orders of magnitude here. Next slide, please. And the next thing we did then was to say, okay, now we're comfortable that we've defined the reservoir properties and we've also defined how the well was completed, because to a great extent, the injection of the CO2 is going to go into the stimulated reservoir volume. It will go somewhat into the matrix, depends on how long and at what pressure you do, but the great bulk of the CO2 that's injected stays in the stimulated reservoir volume. So we started the injection after well had produced for 5 years, and it had produced at that point about 80% of its estimated ultimate recovery that I showed you earlier. And what we did was then we started injecting CO2 in cycle 1, about 5 million cubic feet a day for 2 months. We limited the pressure to 4,300 PSI, but that took the whole system above miscibility pressure, given the composition of this oil. And that's a key part of the recovery mechanism that's taking place, in addition to improving the pressure drive, swelling the oil, and lowering the interfacial tension a little bit. Okay. It was followed by 2 weeks of soak and then 6 months of production. And then we did 11 more cycles of injection, soak, and production. And then we took the CO2 that was produced in that 12th cycle and put it back into the reservoir as part of a 13th cycle and shut in the well, because we're interested in the storage aspects, particularly, and a large amount of CO2 gets stored in that last cycle. I'm going to look at that on the next slide. Okay, so for the DJ Basin, Niobrara, there's opportunity to store basically 1.5 billion metric tons, and you can produce over 3 billion barrels of oil. It does provide an additional storage option around large point sources of CO2. Alex showed some of that on the Colorado and the Wyoming map, and particularly those near Denver, Colorado, and north of there. And then just want to reiterate that the carbon intensity of this oil, its full carbon intensity is 87 grams per megajoule. You store 75 grams, and you have a net of 12 grams of CO2 per megajoule of oil. Okay, let me move on to the next slide. Cana-Woodford Shale in the Anadarko Basin. The next slide. All right, you can see that it's basically, if you look on the location map on the right, it's in the western portion of Oklahoma and laps over into the panhandle of Texas. It's a Devonian age shale. You can see the strat column on the left-hand side. And it's a very basically an ancient shale that has had time to mature. Next slide, please. Again, we put together key reservoir properties. You see the shale depth, and it again it gets quite deep on the western side of the basin, gets down to 12 to 15,000 feet along the edge on the west. It gets shallower to the east, and the oil windows tend to be along that eastern part of the basin. And you can see the thermal maturity basically follows that, where you get really into the higher thermal maturities in the red on the western side of the basin, and the oil windows around Kingfisher and Canadian counties on the right. And we carved this area up into 5 distinct areas. Next. You can begin to see that the early development took place in Canadian County, and that's how it got its name, Cana-Woodford. And on the right-hand side, shows the drilling history. It was quite active, between 2011, 2013. That kind of been back and forth, and then activity really started to pick up in the last couple of years, except for 2020. Next slide. And again, we developed a type curve. This represents 87 wells that have been drilled recently into this part of the basin. You can begin to see that in the dashed line is our matched. There's always a lag time because the first year typically only represents half a year of production. And you basically have, this is a rather deep setting, 9,100 feet, good net pay, and you would expect to recover over 300,000 barrels of oil just on primary production. Then what we did was to take it through the exact same kind of reservoir modeling, history matching, and then the process of injecting CO2 in the various cycles and shutting in the well at the end. And this is what we arrive at. Next slide. Let me just give you a little bit on the reservoir properties for these 5 areas. We talked about the core area. And what you basically see is that these are, to a large extent, relatively light oils and you can see that from the formation volume factors and the volumes of gas, the gas oil ratios. And so they're particularly attractive for doing injection of CO2 in a miscible type of mode. And the depths, 12 to 13,000 feet, give you plenty of room for building up the pressure. So the next slide. Again, we identified a large capacity storage option, nearly 1 billion barrels. It would give you 1.7 billion barrels of associated recovery. And the storage is basically particularly important here because the traditional formation in the Anadarko Basin for storing particularly produced water has been the Arbuckle Formation. And it has taken massive volumes of water because this is a historically great area of oil and gas production from conventional oil and gas reservoirs. And in portions of the basin, it raised the reservoir pressure sufficiently to actually create induced seismic activity. And basically the commission, Oklahoma Commission, then basically put certain constraints and put some restrictions on areas where you could then re-inject. So this gives you another large storage option that would be really important in this area. And then this is an area, if you kind of look at how much you store per barrel of oil, you find that you end up with a slightly negative carbon intensity of 5 grams per megajoule. So let me stop and let Graham cover the Mowry Basin, and then I'll say a few words at the end.
Thank you. All right, looks like my screen should be shared at this point. So we basically tried to model this the exact same way that ARI did. So a lot of the details will be specific to the Mowry Shale and the Powder River Basin, but the methodology is the same. So the first thing to talk about is where are we at in the world? If you look at the location map on the right, the Powder River Basin takes up the northeastern portion of Wyoming and the southeastern portion of Montana. It's important to note that this study looks at just the Wyoming portion of the Powder River Basin, mainly because there's not a whole lot of Mowry potential up in Montana. And then, of course, the Mowry is a siliceous shale that is Cretaceous age. The importance of siliceous is it's got a lot of silica in the rock, and it fractures easily. And so if you go out to an outcrop of the Mowry Shale, it sounds like and kind of feels like walking on broken porcelain plates. It fractures very easily. The next slide is on the left side, we're looking at the depth to the top of the Mowry Shale. The Powder River Basin is an asymmetrical basin, which means it deeps very shallowly on the east and very steeply on the west. And so the dotted line is the basin axis, so you can see how it's skewed towards the west. Gets as deep as the top of the Mowry gets as deep as about 13,000 to 14,000 feet in the basin. And then on the right, we have another thermal maturity map, which is, as Bella pointed out, is a measure of the hydrocarbon generation of that shale. In this case, we've identified 3 hot spots and then a 4th area that is a slightly higher thermal maturity than the surrounding areas. But anything in green or yellow is producing oil. And once you start getting to the oranges and reds, you're looking at more of a condensate, so a very high gravity oil, not quite a gas, but almost. And then this next slide, the map on the left shows those 4 areas that we modeled. Also on top of that, you can see the producing Mowry horizontal wells in the basin. One thing to note is the Mowry is still fairly immature in its development. It's mature in its oil generation, but immature in its development. There's only 45 wells that are producing from the Mowry. So data is a little bit limited. And so going into our type well, normally when you make a type well, you would combine a series of wells to get kind of an average producing well. In this case, because of the quality of the data and just the general lack of data, we decided to go with just using one of the producing wells in the basin as our type well. And this does come from the blue area, which is so far it's where the most activity is in the Mowry. So in this type well, in this case, we're looking at a short lateral, so it's about a mile lateral. It's got 65 feet of pay, and that well is expected to make about 300,000 barrels of oil. Here are some of the stats for the 4 areas as we lined them out. You can see that we use a lot of the same assumptions for the area because we believe that the Mowry is indeed pretty similar across these areas. So we use the net pay thickness of 65 feet, which is the middle Mowry, which is currently what operators are targeting. We use the porosity of 7%, and then we use the relatively high oil saturation of 90%. And then one thing I forgot to mention is if we go back to these slides, you can see there's a red outline in the area. That line represents about 8,000 feet, and that line is actually, it doesn't quite match my 8,000 foot line because it was generated by the USGS in their 2009 assessment of the petroleum system of the Powder River Basin, but it matches better than I would have expected. The importance of that line is below 8,000 feet, the Mowry tends to be overpressured, which is why the operators are targeting that area. And that's also why our geologic areas stop at that 8,000 foot boundary. All right, and so with that said, since that is overpressured, we do use a pretty high initial pressure of 7,000 PSI in our model. And so the findings that we have are we can put in 2 billion metric tons while producing just about 2 billion barrels of oil. But the most important part is right now there is not a well-established saline aquifer for disposal of CO2 in the basin. Currently, the main disposal formation is either going back into the reservoirs from which we produce the water, or there is a Madison aquifer, but it's very deep. It tends to be in the order of 18,000 feet deep, and it is fresh water. And even though it's not currently economic to use for fresh water, you don't want to pollute freshwater sources if you can help it. And so this would give us the ability to put some, put some CO2 away in a shale, which would then also help us get some oil out. And then most exciting is this does look like it will have a pretty massive ability to take this CO2. And so we can put, as I said, we can put about 2 billion in, make about 1.9 billion barrels of oil, but that's a net storage of about 180 grams per megajoule of CO2, grams of CO2 per megajoule. So it looks very exciting. I think with that, I'll go back to Velo.
Thanks, Graham. That was a nice summary. It doesn't fully reflect the tremendous amount of work that has gone into it. And you kind of skipped over some of the more sophisticated parts of the reservoir modeling and things like that. But just in terms of time, it was very similar to what was done in the other two studies. I appreciate that, but did want to acknowledge that there was a lot of work that it went into it, both by you and Eric, and then Stephen Whitaker as well. And we want to acknowledge the support we received from the US Energy Association, both in terms of financial side, but also the feedback that came from our providing draft versions of the study, and then getting a good guidance on how we could strengthen it, certain areas that we could bring out as being particularly interesting to the members of the USEA and the general community. And of course, Graham, it was a great pleasure to be able to work with you guys at the Enhanced Oil Recovery Institute, like always.
Yes, no, thank you.
So with that, we'll turn it back to you, Alex or Michael, for any Q&A.
Great. Thank you so much, Velo. Thank you so much, Graham. Just some really great work that you all did and have presented today. I'd be remiss if we did not thank the U.S. Department of Energy's Office of Fossil Energy and Carbon Management, in particular Joe Giovi, who manages the project, the agreement for us. And that's really where the financial support comes from. So we should acknowledge their support. We have had a few questions come in. So I will start with the first one. Velo, you mentioned the induced seismicity from the injection of water. Is that a concern with CO2 injection as well? Well,
it can be if you don't do it right. I think that's what it comes down. Recall, we limited our injection of CO2 pressures to 4,400 PSI. That's well below any kind of frac pressures. There are several thousand PSI below frac pressure in this area. So that's the main issue, is to stay comfortably below basically frac pressure, which would then begin to create seismicity. So if you do it right, my answer is you shouldn't have to worry about it, but you should do it right.
Thank you, Velo. I find that's a question that comes up a lot in the context of CO2 storage. So that's a very helpful answer. I have another question that came in. Oh yes, regarding the slides and the presentations, and we are recording this webinar, and we will post it in the next day or two onto the event page. Also, it should be noted that the report itself can now be accessed on the event page as well. So please feel free to take a look at those. Now we have another question that came in. How close is this to commercialization? What type of barriers are we looking at? Regulations, access to CO2 costs, a lot a lot in one question there. But
Graham, you want
let
to take
give
a
it
first shot, and then I'll follow up.
Yeah, because the good news is we already have a pretty big CO2 distribution system in Wyoming. The bad news is all the CO2 is accounted for. So we are putting CO2 in the ground for enhanced oil recovery in more conventional reservoirs at Salt Creek Field, which is just north of us here at Casper. And then the other big one that I can think of off the top of my head is Bell Creek, which is the one kind of major field in southeastern Montana. But so, I mean, I think the proof of concept is there. Right now, sourcing the CO2 is the difficult part. It's all taken up right now.
Great, thank you, Grant. And regarding the kind of regulation part of that question, that is another area that USEA has worked on, and we do have a couple of studies that we've worked with the University of Wyoming, West Virginia University, as well as the Cadmus group. Those three groups looked at a series of state policies and regulations in regards to CO2 storage, CO2 EOR, CCUS in general. So I do encourage you to take a look at our website. You can access those reports. We've covered about 23 states so far. We will look to cover some more in the next year or two. But we found that state policies and regulations can differ really widely from state to state. So if you are interested in developing a CCUS project, or if you're a policymaker or know one, highly suggest taking a look at those.
Yeah, and that's actually a good point. I did forget to mention that in Wyoming, I'm not sure if other states have adopted this yet, but we actually have a group put together called the Wyoming Pipeline Corridor Initiative, and they have gone through and worked with the BLM and state agencies to try to basically get a corridor where the hurdles to getting these pipelines permitted will be a little lower. They took into account any surface waters, any potential wildlife impacts. And so the goal with that was to kind of have just a little area where if you want to put a pipeline in, the bar is a little lower there. But generally speaking, yes, getting a pipeline permitted is a challenge, but there are ways to mitigate it.
Yeah, I made a comment on an earlier webinar today that the pipeline infrastructure issue in this country is pretty similar to kind of the transmission infrastructure issue if we're discussing renewables. I think the infrastructure for both probably not talked about enough, and yet incredibly important to the success of CCUS in the United States.
Alex, my computer froze, and so I've become Joyce Frank. Can you hear me and see me?
We can hear you and see you. Yes.
I wondered what that was all about. You had some kind of new science over there in your building.
Yeah. I apologize. It happens occasionally.
Yeah, before Alex takes, we've had a couple more questions that are good ones coming in. Alex is going to grab those, but I think just something that some of the members of our audience might appreciate. If they've been tracking CO2 EOR as a storage medium or CO2 storage in brine, there's a certain mechanism that's been talked about a lot. For shale, it's going to be a different mechanism. And could you kind of give a simplified insight to why shale could hold the CO2 other than just by the fact you've pushed it down in and you've capped off the pipe?
Sure. Let me take a quick shot. I'll have Graham follow on that. Basically, what during the primary production of the oil, the first 5 years, you've created, in a sense, pulled the pressure down, or if you want to think about it, space. And so now you have some room, or at least pressure-based room, to inject CO2 into that area. And the CO2 is less dense. It'll move, past that early oil and begin to move towards the edge of the stimulated reservoir volume. And then as you pull begin to produce, remember doing a cyclic type of mode, some of that CO2 gets trapped in the pore space. And you continue that process, and each time you put CO2 in, more of it gets trapped in the pore space. If there's water around, some of it goes into solution into the water, and whatever oil is there, the CO2 will go into solution with the oil as well. And then at the very end, you put in the last volume of CO2 that has come back, and you shut in the well. And then that CO2 will basically equilibrate with whatever is left behind in that stimulated pore space. And over time, it becomes just a single phase in solution with the remaining oil and fluids. Graham, you want to kind of add to that?
Yeah, I think the piece that I would add is there is a process that I will admit I don't fully understand, but it's called imbibition. And that is where, so as Vela pointed out, you can store it in the in the void space, in the pores, but also it will adhere to the surface of the rock as well. And so I think that's kind of the key to getting more CO2 in the ground, because it's one thing to fill up the space, but now once you start basically attaching it to the rock, you can really make some headway there.
The reason I brought that question up is I had heard in a previous discussion that there's a certain amount of attraction in the fracture zones to the CO2 molecule itself, where it gets pulled into these fracture zones. The pressure helps push it in, but there's also an additional uplift taking place that we would not see in your typical main pay zone CO2 EOR or ROS EOR or brine for that matter.
Yeah, natural fractures as well as, of course, the induced fractures are a critical part of both the production mechanism and particularly the storage mechanism, and how far into this pattern area that CO2 will be able to go, and like Graham says, to imbibe would be a good word for that.
Right. So one last piece, and I'm going to flip it back to you here, Alex. If I go to a main pay zone and I produce and I've done a water flood, I always have to keep in mind what my original discovery pressure was, especially if I'm going to do gas storage, a completely different issue. With shale, how does original discovery pressure play into this? Because it's a lot different than when we go to a main pay zone in a typical conventional EOR setting.
Graham, go ahead.
I'm trying to think.
That's a tough one.
Buy me some time. Honestly, I don't know. Let me think about.
Sorry about that. I didn't. It was the reason I brought the question up is that if for natural gas, if I'm going to store gas in a depleted gas reservoir, I really have very little latitude to overpressurize, if at all, the original field. So I'm constrained by the original discovery pressure. So I'm going to go over here to EOR, and there's some certain variables. And one of the big concerns with conventional CO2 EOR and storage is overpressuring the original discovery pressure of the field, because obviously we push the CO2 beyond places where it would have otherwise gone. And I was curious how that might work in shale. But we could we could probably do another webinar on it.
Let me address that. One of the good things, which also helps, of course, on the production side, is many of these reservoirs, because they are highly mature, have a strong seal, are overpressured to begin with. And so you can raise the injection pressure and the storage pressure somewhat higher without exceeding the original overpressure. You still want to stay well within the limits of fracture pressure, but these reservoirs have accommodated very high pressures, overpressures, and that gives you that extra boost that you don't have in a conventional, normally pressured oil field or residual oil zone. So that's that extra, if you want to call it, boost that you get. And that's very important. For the higher the pressure, the easier the miscibility mechanism is, the more CO2 you can put into solution with the oil, and the whole system works a lot better.
Got it. Thank you for clarifying all that. And we have kind of an additional comment that the CO2 will absorb strongly to organic matter in the shales and to a lesser extent clays. So wanted to mention that follow-up comment.
That's a very good comment. That both Graham and I should have talked a little about that. There is just like, methane gets absorbed into coal, which is the primary storage mechanism. Now, coal is what, 90% carbon, has some dirt in with it, but in the shales, you might be looking at, what do you think, Graham? 4, 5, 6, maybe in the Bakken, maybe 10% type of organic matter. So it is, you do have that extra storage mechanism of absorption into the shales, but it's not as dominant as it is in something like coal bed methane.
Great, thank you for further clarifying that. Now, another question that came in, have you considered the temporal nature of CO2 absorption?
That's a good one for you, Graham.
No, I have not. I guess I'm not sure what you mean by temporal or temporary. I guess if it's temporary, well, sure, but that's the point, is that we would shut these wells in at the end of this cyclic process, and so therefore, as long as we don't have it open to the atmosphere, it's not going to come back out. And I don't expect it to migrate the hundreds of miles it would take to get back to the surface through outcrops.
Yeah, I recall when we talked about there's that stimulated reservoir volume and then the matrix, and there are 2 to 3 orders lower permeability in the matrix. Okay, so it'll pretty much stay within the stimulated reservoir volume. You would have shut in the well and cemented and properly PNA'd it. And so that, if you do it right, that keeps it from coming up the wellbore. In terms of lateral migration, it's not going to go very far because the permeabilities in the matrix are so low, it'll stay in the areas that have been hydraulically stimulated. And then over time, basically, it just equilibrates with the rest of the reservoir that's in place.
Got it. Thank you. Another question, what changes to pad design need to be made in order to support the CO2 injection process?
Well, I guess I don't, of course, I'm a geologist, not a facilities engineer, but I know some of the key things that you'll have to do in these fields is you will have to use stainless steel pipe everywhere. CO2 will just eat right through regular steel. And as far as on the surface, I suppose you'll have an extra compressor facility to condense the gas so you can get it down the hole. But other than that, it's, those are 2 big things, but it's not complicated beyond that.
Yeah, and a distribution system for the CO2, and make sure that as well is protected from corrosion.
Got it. Thank you. Now this question is maybe more opinionated, or requires more of an opinion to answer versus a technical answer to it. But would love to hear your thoughts on whether the oil industry can survive coming carbon constraints without CO2 EOR.
My opinion is no, we can't. As I was saying to the panel before we got on the live seminar, I think we've already waited too long as an industry, and so now we get to we've been given the rules, and now we have to find a way to play with them.
Yeah, I there is, the markets and the public are pressing for low carbon energy. This is one of the pathways for getting to that. Storing as much or more CO2 than is in the oil that's produced, trying to get to low carbon intensity oils. And, of course, if you go to gas, you've got the great option of going to hydrogen. Then you do have to capture and store the CO2. So it has probably a little easier pathway, I think, in terms of storage. For on the oil side, that'll, just like Graham says, become very important.
And Mike, do you have any thoughts on kind of the role that ESG, CSR stakeholders may play in pushing for CO2 EOR?
Well, there's like even before this was an environmental question to ask, there was always several different camps around why bother with CO2 EOR in the first place, or the issue of the CO2 resource that was being used, that could be used. There are operations industrially driven that need to find a solution for CO2 that they have no other means to do but to move it out to a marketplace somewhere for long-term storage or sequestration. The EOR part, in the end, probably will not be the dominant source of storage, but the extra revenue value that you can get at the front end is part of the extra uplift that helps infrastructure get built. States put time and money and effort into the regulatory structures, and that people who have assets that are at risk, as with emission streams, can get some benefit for capturing some of the higher costs at the front end. Over time, most of the CO2 will probably end up in the larger brine type settings. If we're not going to be driving cars with gasoline engines in them in 30, 40 years, and it's a moot point. So on the ESG CSR side, there's a number of different indexes. The companies that have any kind of relationship to fossil fuels consume, produce, emit, what have you, own, are indexed, and depending on how CO2 EOR storage is viewed by the different index providers, could have an impact on what kind of carbon mitigation these different industries that are being indexed will benefit from or not. So there's a lot of moving pieces on that. And like anything else, there's camps that are very supportive, and there's camps that for the last 20 years have said this is a waste of time, period. So, pick your market, pick your industry, pick your process, and you're going to find how this lines up. If you're a state, there's a tremendous amount of resource produced right, puts value back into the states and creates jobs, while you're also mitigating greenhouse gases. For federal lands, one could argue that this could have a role to play or not. And for stakeholders or shareholders, there could be value here. One other part of the CSR ESG piece that's very important now, that is expressed, we'll see and hear a lot more, will be the environmental and social justice part of this. One thing about CO2, EOR in any kind of form or fashion is it's typically not found in urban areas or cities. So it's typically deep rural. So the regional impact on people is I won't say it's non-existent, but it's limited. The impact on environmental situations, if it's already been touched with prior production, it's a brownfield that you're going to clean up with new permits and regulations to operate, where a lot of your mature fields that are not shale have been in existence for a long time. There's a lot of remediation in these brownfields that CO2 EOR brings. So maybe regional economic development and a redress of social and environmental justice. For shale, almost everything that's been done on the shale side is done under new rules and regulations probably put together in the last decade. And so you've got new gear, new equipment. You do not have the legacy issues of mature oil fields and other things that go with that. If there's any kind of environmental remediation that needs to be done on shale side, will have been identified at this point before the CO2 goes down into it. So CSR, ESG will have a role to play, and some people will find it acceptable, and some won't.
Great, thanks, Mike. So we are at time. I'm going to take two more questions here, and then we'll call it. Apologies for those who didn't have their questions addressed. But interesting segue from what you were just saying, Mike. Would CO2 storage in shales be economic for consideration of dedicated storage? So skipping the first 12 cycles of oil production.
We did not look, it was not in the scope of work to look at the economics. Love to do that as a next step. If you hark back to what just Mike said, this is a well that's been just only 5 or 6 years old, so it's in good shape. You may have to convert the tubing over to stainless steel, but you don't have to re-drill the well. You need to basically bring in a compressor, and hopefully it's a compressor that would serve a number of wells in a setting. Off of a pad, you might hopefully serve, 6 or 8 wells together. And then you need a source of CO2. And, that's, you'd want to look at, what the distance is that CO2 would need to come for. But like you early showed, Alex, those dots are pretty much overlay the basins. So they're not that far away. And so then you operate the well. And so you avoid much of the early capital costs required to drill new wells. You basically, you'll produce kind of the rest of the primary oil along with the cyclic oil. So your operating costs don't go up much beyond the compression and the injection and reinjection part. But it does matter how efficiently the well has been prepared, and has the operator given thought ahead of time to make sure that the geologic setting is going to be favorable, and they maintain that favorability during the development of the primary production.
Got it. Thank you, Velo. And it sounds like a great topic for another study. So we're always looking for new ideas for that. So thank you to whoever submitted the question. Final question, and then we're gonna go ahead and call it. What additional permitting will be required? Does this change the well classification? And as I understand it, EOR operations require a class 2 classification, whereas pure geologic storage requires class 6. The class 2 process is, I would say, much more efficient, shorter time frame, less costly. Class 6 is a pretty expensive and time intensive process. But anything to add to that, fellow Graham?
Graham, why don't you take that, because you guys, Wyoming has been given primacy for class 6, so.
Sure, yeah, I would just be able to echo what Alex said. Yes, it is a class 2 permit for EOR. It's class 6 for sequestration. Right now, the process is much more difficult and much more expensive for a class 6 permit. So, well, there it is.
Yeah,
And
an
I don't even know if
original
we have
well
any
would have been drilled to class 2 standards, and then you go back to just like you would go for enhanced oil recovery, an application to the state to basically continue that use of that well under a CO2 injection mode.
Great, thank you for that further clarification. Well, with that, we are 6 minutes over our time. Velo, Graham, just great job. Thank you so much. The report is fantastic. Again, to reiterate from earlier, the recording of this will be posted on the event page in the coming days. The report is already posted, so certainly recommend everyone take a look at that. Thank you again. Mike, do you have any closing thoughts?
Nah, just Vela and Graham, thank you guys very much for the time today, for the work on the study. I think that I'm sure will provoke some additional feedback coming to you from people that have gotten hold of the study or have watched this. And as always, Vela, it's great to work with you. And Graham, great to meet you. And Alex, thank you as well. And to the folks at DOE.
All right. Thanks all. Have a good rest of your week. And everyone stay safe out there.
Thank you.
Thank you.